Hello and welcome everyone. Today we will be discussing the different types of energy storage cells, including lead acid, lithium ion, and nickel metal hydride, as well as the calculation of battery charging and discharging. Energy storage solutions are an essential component of renewable energy systems, and understanding the different types of energy storage cells and their energy charging and discharging behavior is critical for achieving high levels of performance and efficiency. We often get puzzled by announcement of new batteries that are said to offer very high energy densities, deliver thousands of charge and discharge cycle and are paper thin. Are they real? Perhaps, but not in one and the same battery. While one battery type may be designed for small size and long runtime, this pack will not last in wear out prematurely. Another battery may be built for long life, but the size is big and bulky. The third battery may provide all the desirable attributes, but the price would be too high for commercial use. Battery manufacturers are well aware of customer needs and have responded by offering packs that best suit the specific applications. The mobile phone industry is an example of clever adaptation. Emphasis is placed on small size, high energy density, and low price. Lovability comes in second. Now we'll see the cell types. There are several types of energy storage cells commonly used in renewable energy systems, including lead acid, lithium ion, and nickel metal hydride. Let me tell you about lead acid invented by the French physician Gaston Plante in 1859. Lead acid was the first rechargeable battery for commercial use. Today, the flooded lead acid battery is used in automobiles, forklifts, and large uninterrupted power supply UPS systems. During the mid 1970s, researchers developed a maintenance free lead acid battery that would operate in any position. The liquid electrolyte was transferred into moisture separators and the enclosure was sealed. Safety valves were added to allow venting of gas during charge and discharge. Driven by different applications, two battery designations emerged. They are the small sealed lead acid SLA, also known under the brand name of gel cell, and the large valve regulated lead acid BRLA. Technically, both batteries are the same. Engineers may argue that the word sealed lead acid is a misnomer because no lead acid battery can be totally sealed. Because of our emphasis on portable batteries, we focus on SLA. Lead acid batteries are the oldest and most commonly used type of battery. They are reliable, durable, and relatively inexpensive, making them a popular choice for renewable energy applications. However, they have a low energy density and are not as efficient as the other type of batteries. Lithium ion batteries are a newer type of battery that has become increasingly popular in recent years. They have a different, higher energy density and more efficient than lead acid batteries. They also have a longer lifespan and can be charged and discharged more quickly. However, they are expensive than lead acid batteries. The energy density of the lithium ion is typically twice that of standard NICD. Improvements in the electrode active materials have the potential of increasing the energy density close to 3 and behave 3 times that of nickel cadmium. In addition to high capacity, the load capacities characteristics are reasonably good and behave similar to NICD in terms of discharge characteristics. similar shape of discharge profile, but different voltage. The flat discharge curve offers effective utilization of the stored power in a desirable voltage spectrum. The high voltage allows battery packs in only one cell. Most of the today's mobile phones run on a single cell, an advantage that simplifies battery design. To maintain the power, same power and higher current are drawn. Low cell resistance is important to allow unrestricted current flow during load pulses. The lithium ion is a low maintenance battery, an advantage that most other chemistries cannot claim. There is no memory and no scheduled cycling required to prolong the battery's life. In addition, the self discharge is less than half compared to NICD, making the lithium ion well suited for modern fuel gauge applications. Lithium ion cells cause little harm when disposed. Despite its overall advantages, lithium ion all has its drawbacks also. It is fragile and requires a protection circuit to maintain safe operation. Built into each pack, the protection circuit limits the peak voltage of each cell during charge and prevents the cell voltage from dropping to too low on discharging. In addition, the cell temperature is moistened to prevent temperature extremes. The maximum charge and discharge current is limited to between 1C to 2C. With these precautions in place, the possibility of metallic lithium plating occurring due to overcharge is virtually eliminated. Nickel metal hydride batteries are a middle ground between lead acid and lithium ion batteries. They have a higher energy density than lead acid batteries and are more environmentally friendly than lithium ion batteries. However, they are less efficient than lithium ion batteries and have a shorter lifespan. Let me tell you more about lithium metal hydride battery. Research of nickel metal hydride battery system started in 1970s as a means of discovering how to store hydrogen for the nickel hydrogen battery. Today, nickel hydrogen batteries are mainly used for satellite applications. They are bulky, maintain high pressure steel canisters, and cost thousands of dollars per cell. In the early experimental days of nickel metal hydride battery, the metal hydride alloys were unstable in the cell environment and the desired performance characteristics would not be achieved. As a result, the development of NIMH, that is nickel metal hydride, slowed down. Now, hydride alloys were developed in the 1980s that were stable enough for use in a cell. Since the late 1980s, NIMH has steadily improved. The success of NIMH has been driven by its high energy density and the use of environmentally friendly metals. The modern NIMH offers up to 40% higher energy density compared to NICD. There is potential for yet higher capacities, but not without some negative side effects. The NIMH is less durable than the NICD. Cycling under heavy load and storage at high temperature reduces the service life. The NIMH suffers from high self discharge, which is considerably greater than that of NICD. The NIMH has been replacing the NICD in markets such as wireless communications and mobile computing. In many parts of the world, the buyer is encouraged to use NIMH rather than NICD batteries. This is due to the environmental concerns about careless disposal of the spent battery. Experts agree that the NIMH has greatly improved over the years, but limitations remain. Most of the shortcomings are native to the nickel based technology and are shared with the NICD battery. It is widely accepted that NIMH is an interim step to lithium battery technology. In addition to the lead acid, lithium ion, and nickel metal hydride batteries discussed earlier, there are other types of energy storage cells that are used in renewable energy systems, such as sodium ion and flow batteries. Sodium ion batteries are similar to lithium ion batteries but use sodium ions instead of lithium ions. They have a lower energy density but are more abundant and cheaper than lithium ion batteries. Flow batteries are a type of battery that use a liquid electrolyte to store energy. They have a longer lifespan than other types of batteries and can be charged and discharged more quickly. They are also more flexible in terms of capacity, making them suitable for large scale energy storage applications. Now, we'll move on to the second part of the video, that is battery charging and discharging calculations. Battery calculation and discharging calculations are essential for ensuring the proper operation of energy storage systems. The following equations can be used to calculate the charging and discharging of batteries. Charging time is equals to battery capacity divided by charging current, whereas the discharging time is equals to battery capacity divided by discharging current. For example, if a 100 Ah battery is being charged at a rate of 10 amperes, the charging time would be 10 hours. Similarly, if the same battery is being discharged at a rate of 5 amperes, the discharging time would be 20 hours. It is also important to consider the depth of discharge, that is DOD, when calculating the battery charging and discharging times. The depth of discharge is the percentage of battery's capacity that has been discharged. For example, if a 100 Ah battery has been discharged by 50 Ah, the depth of discharge would be 50%. The following equation can be used to calculate the battery's remaining capacity. Remaining capacity is equals to the battery capacity into 1 minus depth of discharge. In conclusion, battery storage solutions are a critical component of renewable energy systems. Understanding the different types of energy storage cells, including lead acid, lithium ion, and nickel metal hydride, and their discharging and charging behavior is essential for achieving high level of performance and efficiency. By using the proper equations and consideration of depth of discharging, it is possible to accurately calculate the battery charging and discharging times and ensure the proper operation of energy storage systems. In addition to the equations discussed earlier, there are other factors that can affect the battery charging and discharging times, such as the temperature and the state of charge, that is denoted by SOC of the battery. The temperature can affect the battery's charging and discharging efficiency, with lower temperatures resulting in slower charging and discharging times. It is important to consider the temperature when calculating the battery charging and discharging times and to ensure that the battery is kept within the optimal temperature range. The SOC that I said earlier, the state of charge, is the amount of energy stored in the battery and that can affect the battery's charging and discharging times. As the state of charge approaches 100%, the charging rate will decrease and the battery will take longer to charge. Similarly, as the SOC approaches 0%, the discharging rate will decrease and the battery will take longer to discharge. It is also important to consider the efficiency of charging and discharging process when calculating battery charging and discharging times. The efficiency can be affected by factors such as the charging and discharging rate, the temperature, and the type of battery. And that's a wrap up. Thanks for watching and see you in the next video.